let's start talking about the magnitude systems. So in this video, we're going to be discussing how it started and what the magnitude scale is. We're going to cover the difference between apparent and absolute magnitude, and then we're going to talk about the distance modulus formula that connects apparent and absolute magnitude. So first, let's read this. The idea of a magnitude scale dates back to Hipparchus, who invented a scale to describe the brightness of the stars he could see. He assigned an apparent magnitude of 1 to the brightest stars in the sky, and he gave the dimmest stars he could see an apparent magnitude of 6. So here's a chart that basically shows he assigned the brightest stars as 1, and then all the way down to 6. And on the side over here, you can see that the brightness of the brightest star, we define it as exactly 100 times the brightness of the stars with magnitude 6. So we took from this and we created our own magnitude system, our own modern magnitude system, based off of Hipparchus's observations. So now let's look at this diagram. Here it shows the magnitudes all the way from 30 to negative 30. And one thing to keep in mind is that the brightest stars go on this side and the dimmest objects in the sky go on this side. So it might be a little counterintuitive at first, but the more negative a star is, the brighter it actually appears in our sky. For reference, we can see some things like the sun is at negative 26.7, our full moon is at negative 12.6, Venus at its brightest is at negative 4.4, Sirius, which is the brightest star in our sky, is negative 1.33, Polaris, which is our North Star, is at 2. Our eyes can see as far as 6, which is how Hipparchus got his 1 through 6. And the Hubble Space Telescope is at a 31.5. So just as reference, this is based off of this description. This is how we can fit some of the common objects into a magnitude system. Now let's start by talking about apparent magnitude. So for the definition of the apparent magnitude system, this system helps us compare stars how we perceive them. So that's the definition. Now there's a formula that can relate the apparent magnitude of a star with its brightness. And the formula goes like this. The magnitude of the first star minus the magnitude of the second star equals negative 2.5 log base 10 with the brightness of the first star divided by the brightness of the second star, or the ratio of the two brightnesses of the stars. This can come in handy when we have to find a brightness of a star when we're given the magnitude, or if we have to find the magnitude of a star given the brightness. Like, what is the flux / brightness of a star of apparent magnitude 1? Let's start plugging into our formula and see what we get. So we have, let's say M1 equals 1. M2 we don't have. B1, this is what we need to find, and M2 we also don't have. So right now we're not able to solve this question because we only have one of the 4 variables in the equation. In a situation like this, what we can use is use our own sun as a reference. So in our last video, we found that the brightness of the sun, of our own sun, from respect to Earth is 1,385 watts per meters squared. Watts per meters squared. Okay. With this information and the information right here, which is the magnitude of the sun, let's use that as well, negative 26.7. We can plug these in to the formula, and now we will have 3 of the variables in this formula. We just need to figure out this one. That's doable. Okay, I just moved the numbers up here, and now let's write the formula. So we have M1 minus M2 equals negative 2.5 log B1 over B2. And we're using our sun for the second star. Now let's start plugging into the formula, and we'll have 1 minus minus gives you plus 26.7. equals negative 2.5 log B1 over B2. Now we want to, I can plug in B2. 1385. Now we want to isolate for B1, so let's do that. And I went ahead and did the rest of the calculations by myself, but from a calculator, we can get the answer as 1.15 times 10 to the power negative 8 watts per meters squared. And that's our answer. It's not very difficult. Just take the numbers that you're given and plug it into the formula. And when you're only given one piece of information and another star is missing, you can use our own sun as a reference. So now let's move on to absolute magnitude. This is a bit different. How we're defining this is apparent magnitude is based off the real distance and how we perceive it. Absolute magnitude is assuming that the star is 10 parsecs away from the Earth. So every single star we're comparing will be at the same distance. So we define 1 parsec, which is written PC for short, as 3 times 0.86 times 10 to the power 16 meters. This is a unit of measurement that we use in space, like light years, astronomical units, etc. But we'll talk about more exactly how a parsec comes from in our next video. So let's write this definition down. The absolute magnitude system compares stars to how they actually are by themselves, making distances irrelevant. The absolute magnitude formula is very, very similar to the apparent magnitude formula. There's just a slight difference where we have capital M1 minus capital M2. That's the convention. Apparent magnitude is lowercase m and the absolute magnitude is uppercase M. Equals negative 2.5 log base 10. Everything's the same. This is where we change. We have luminosity of the first star divided by luminosity of the second star, where before we had brightness and brightness. Now let's use this formula in an example problem. So what is the luminosity of a star if it has an absolute magnitude of 2.3? And note that the absolute magnitude of the sun is 4.83. And remember, this symbol always means sun. So we have to find the luminosity of the mystery star. But we are given the absolute magnitude of 2.3. We know that the absolute magnitude of the sun is 4.83. And remember, the apparent was negative 26.7. And from our last problem, we know that the luminosity of our sun is 3.896 times 10 to the power 26. Now we can plug these into our formula, just like we did before. So we have M1 minus M2 equals negative 2.5 log L1 over L2. Let me skip ahead for you guys. Okay, I've isolated for L1, and we get our final answer from our calculator, 4.005 times 10 to the power 27 watts. That's our answer. And that is the luminosity of the star described. Now that we've talked about absolute and apparent magnitude systems, let's recap by comparing the two. So we have our apparent magnitude, which is taken from the actual distance away, and we have our absolute magnitude that is taken from 10 parsecs away. So this one obviously compares based on how we perceive them, while in absolute magnitude, the distance is irrelevant. Now in the formula, apparent magnitude takes flux, which depends on distance, and the absolute magnitude formula depends on luminosity, and this one does not depend on distance. As convention, we would use lowercase m for apparent magnitude, and for absolute magnitude, we use uppercase m. Now for what they have in common, both use a similar formula, and both put stars on a scale to compare them with each other. Now let's move on to distance modulus, which combines both magnitude systems to find how far away a star is from us. Let's start by writing the definition of distance modulus. So this is a formula that relates the difference in apparent and absolute magnitude of a star to its distance from the observer. So let's write down the formula. So we have apparent magnitude minus absolute magnitude equals 5 times log base 10 of the distance minus 5. This d right here, this distance is in parsecs. So let's look at how to apply this. So if a star has an apparent magnitude of 9.5 and an absolute magnitude of 4.5, let's calculate the distance to the star in parsecs. So this should be very simple. We just plug in the lowercase m and capital M. We would have 9.5 minus 4.5 equals 5 log distance minus 5. So what do we have on this side? We have 5 equals everything else. So let's start isolating for d. We end up with 2 equals log d. In other words, d equals 100. And that's it. That's our answer. D is 100 parsecs. So the star is 100 parsecs away from the observer. Now, why does this make sense? If a star is 100 times further, it should look like it's 100 times dimmer as well. And you can see that the difference between this and this is 5. If you go all the way back to the top, the brightest star is 100 times brighter than the dimmest star in Hipparchus's magnitude scale. And the difference between 1 and 6 is also 5, right? So this is why we get such a perfect number of 100 parsecs. Let's look at our next problem. If a star is 200 parsecs away, what would be its apparent magnitude if its absolute magnitude is 3? So this is backwards. We have to do this the other way around now. We have to find m given absolute magnitude and the distance, which is 200 parsecs. Let's solve for m. And from our calculator, we get an apparent magnitude of 9.51, and that is our answer. So we talked about the magnitude systems, how it came to be, the difference between apparent and absolute magnitudes, and the distance modulus that relates the difference in apparent and absolute magnitude to the distance from its observer. I'll see you in the next video. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.